Welcome to Group 2's Curves and Surfaces video by John, Raj and Dan. Episode 1, Sir John's Dilemma. Starring Sir John of Wallington and Lord Ronald of Camelot. Why does mathematics have to be so difficult? A map is called smooth if gamma is arbitrarily what the... Ugh! What's this nonsense? I need to seek help. I know. Lord Ronald of Camelot can be of my assistance. Oh! Ronald of Camelot! I have finally found you!
Why, greetings there, my dear friend, Sir John of Wallington. It's been a long time since I've seen you. What brings you here to the Queen's Cave on Dipton Burn?
Well, I have run into some trouble on a mathematics problem set upon me by the Queen Mary of Scots.
Oh, mathematics? It's been a very long time since I've done that. I can't promise anything, but let me have a look at that for you. Oh, okay. Oh, yes. I remember this. Third year mathematics. Oh, I can see that you have to work out the curvature. Is this correct?
Jolly gosh, yes! I just do not understand what to do. It's about a plane curve in R2.
Well, I'll explain it to you in simple terms. The curvature measures how curved the plane curve actually is. Here, let me show you what I mean by this on this script. Oh, sorry, don't mind him. He's in a rush.
Lord Ronald's script shows him the equation of the curve and then plots it. He then explains how he chose the domain. Lord Ronald chose the domain by ensuring that the curve they have is regular. He goes on to explain that a curve is regular if the speed is not equal to 0 for all values of t. We can see that your curve is regular by doing this simple calculation.
Why is this important, Lord Ronald?
Oh, because it means it has nice properties. This includes unit speed reparameterization.
That's fantastic!
However, Sir John, it involves an elliptic integral.
Why is this a problem, Lord Ronald?
Because they are too hard to deal with.
Okay, Lord, thank you. What about the curvature? My assignment asked me to compute it.
Well, sir, let me show you here.
Lord Ronald explains to Sir John that as long as your curve is regular, all you have to do is use this special equation to find the curvature. And to find the sine curvature, you use this equation. Using these formulas, we find that the curvature is, and the sine curvature is.
Oh, I see. Thank you, Lord Ronald of Camelot. I'm so glad I came to see you. Can you show me a way to find the points where it is most or least curved? Yes? I feel that I will be very useful to the Queen.
Oh, well, okay. Let's walk and talk, shall we? And I'll explain it to you on the way. Now, if you think about it, curvature circles is your answer.
Curvature circles, you say?
Yes, oh Sir John, yes.
Lord Ronald goes on to explain how the smaller the circles, the more the curve curves, and the bigger the circles, the less the curve curves.
Thank you, my lord. That's rather splendid. I've got something else.
Go on.
Basically, we're looking at a space curve in 3 dimensions. How could we obtain our space curve from the plane curve?
Okay. Anything else?
Yes, and about some properties.
John shows Ronald the space curve and similarities can immediately be seen. Ronald then shows John how to check if it is regular. He explains that it is exactly the same as finding out regularity for a plane curve. Using the same formula as before for regularity, we can see that the space curve is regular. Ronald notices that the domain for both plane and space curves are the same. He tells Sir John that it is not unit speed. He then shows him how he can obtain the space curve from the plane curve. By rotating it about the z-axis, you can see that it has 3 coordinates. That gives us the 3rd dimension of the space curve.
That's really helpful. What about the curvature and torsion?
Of course, let me show you. Look over here, will you?
Lord Ronald explains that for the curvature we use the equation, and for torsion, using these formulas we find that the curvature is, and that the torsion is.
Yes, you got it.
But what does torsion even show? I don't understand. It sounds very interesting, but it must show us something.
Of course it does. There's a reason why mathematics is the best subject. Everything has a reason. The torsion can be thought of as how much it bends in the left or right direction out of the plane of curvature.
That's great! Thanks! So a formal definition for torsion could be how sharply is twisting out of the plane of curvature. Cool. So, how about surfaces? What are first and second fundamental forms? And what are the mean and Gaussian curvatures?
Yes, Sir John. Have a look here. I'll explain it to you.
This is your surface. This domain ensures that we have no self-intersections with your surface. We can then calculate the first and second fundamental forms of the surface. Coefficients of the first fundamental form are the inner product of the partial derivatives of your surface. The coefficients of the second fundamental form can be found using these formulas. These are the coefficients that we find. Using these coefficients, we can calculate the Gaussian and mean curvature. The Gaussian curvature and mean curvature formulas are as shown. Using these formulas and the coefficients that we previously found, we find the Gaussian curvature to be, and the mean curvature to be equal to 0.
Remarkable! There's even calculations on there, which I'm going to need for my problem sheet. So our surface is regular when we pick a domain which ensures there's no self-intersections.
Yes, that's correct, Sir John.
So, what about the normal curvature and the geodesic curvature? What are they? How do they differ? Also, can you tell me some, history about my shape?
Yes, of course. Have a look here.
To calculate the normal curvature, we use the following formula, and for the geodesic curvature, we use the other formula. The normal curvature is the rate of change of the normal. The geodesic curvature is the curvature of the projection of gamma on a plane tangent to the surface at the point of consideration, T. Your surface just happens to be a catenoid. A catenoid is a surface in three-dimensional Euclidean space arising from rotating a catenary curve about its directrix. As the mean curvature of your surface is equal to 0, we know that it is a minimal surface. The catenoid is the first minimal surface to be discovered. It was found and proved to be minimal by Leonhard Euler in 1744.